Hello everyone! So I'm going to be doing another video on space physics. This time is on the life and the death of a star. So it actually has a little bit more than that. It's going to be as well how you get all that cloud of dust and gas where you get a star in the middle and then you get a planet formed because there is the accretion of the dust particles that are around the star. So it has a little bit more detail than that, but the focus is how stars are born, how they live, and then how they die. And how they die depends on the type of star. Now, the easiest way to actually, for you to remember this, is to go to this amazing documentary. In half an hour, the documentary is 45 minutes, but in half an hour, you have all the material done. And if you want, go on that documentary, to which I'm going to put the link on the description. Now that link sometimes stops working, but if you just write the name of the documentary, which is from the History Channel, you will always find a new link, okay? Otherwise, this is what you can do. I have here a whole summary of how stars are born, live and die, okay? So if you don't want to see the video, don't watch the documentary, and then instead this is the summary of what happens, okay? So it starts with nebulas. Nebulas are clouds of gas and dust, okay? And they are mainly made of hydrogen gas. Now, the thing that happens is, I cannot give you that much detail on this video alone, only if I would do another video. But the thing that happens is, because of gravity, the particles are going to tend to get closer together, and as they do that, they actually start to have some movement, and then they move faster, and then they heat up. So the gravity and heat that is around the nebula, so you just need the particles to start to be attracted to each other, that they start spiral around each other. You get gravity and heat, and this is the ingredients for you to get the star formation. So you get all this lump of gas starting to move around a circle, okay, move around the center. This takes about 100,000 years, okay? As they start to move around, and you can try this with anything really. If you have something, for example, plasticine, and you get it into a circular shape, a sphere shape, if you move it really, really fast, you are going to see that it's going to become flat. And this is because there is conservation of a certain momentum, an angular momentum. So it's going to become a flat disk moving around really fast. Okay? In that flat disk, that's where the star is going to be born. Okay? And this stage is called a protostar. It's like a baby star. Okay? Then these particles, they keep accumulating, getting closer together, and eventually you get a sphere or a disk of dust and particles around a center. And in that center, you get the main core, where you have the particles. They are now really close together, and they are quite hot. And this is, in the center, the star. And all that disk around is where the planets are going to be formed later on. Because the other dust particles that do not go to the star, they will eventually, as they move around the main star, they will eventually accrete. This is known as the accretion theory. They will eventually accrete and then form lumps of rocks where you get the planets, okay? So, the energy for the star's life, and I'm sorry that I'm not talking about the planets, later on I could, but this is because it's just, this lesson is about the stars, okay? So the energy for the star's life comes from thermal-nuclear fusion, where the star is fusing the hydrogen that is made of into helium, okay? And then during the star's life, what is going to happen is the star is quite big, and again, you have lots of gas, so gravity is going to try to compress all that gas, so it's going to try to collapse the star. At the same time, the star has a lot of heat because of thermal-nuclear fusion. So this heat is going to provide the counterforce, the pressure, okay? So the star's life is a battle in between getting just about the same amount of pressure than what you have for gravity, okay? And if these forces are balanced, then the star is a stable star, and this stage is known as the main sequence star, okay? Most stars, or actually all stars, will spend most of their lives in this stage, all right? Now, other things you need to know about stars. The stars can come with different colors and shapes. So for example, if you have a red dwarf, then it's going to be a small and a cool star, okay? And, apologies, and this star is going to have a large lifespan because they have a smaller mass, and therefore they are not going to have as much fusion happening in their core. However, if I get a star that, due to the amount of hydrogen it had initially, is big, so is large and hot, so it has about 20 sun masses, they will have shorter lives because they have a higher fusion rate. So it means that you have more particles there, gravity is trying to compress the star further, so you need more pressure to balance that out, so you need more fusion of hydrogen to helium. So what happens is the small star, because it doesn't need to provide as much pressure, then doesn't not need to do fusion so fast as, or faster, or as fast actually, than a bigger star, where because gravity is higher, they need to provide a higher force of pressure, and therefore they fuse more, okay? And the reason why fusion, the fusion rates, the amount of fusion that you have over a certain amount of time is going to relate to the star's lifespan is because the star dies when it runs out of fuel. So after the star fused all the hydrogen into helium, then the star does not have enough pressure to overcome the gravity or to counter the gravity. So what is going to happen is the stars, once they run out of their fuel, they are going to die. Now, depending on the big or the mass of the star, the mass of the star, they are going to die in different ways, okay? So, if they are a large star, they die in an explosion. If they are a smaller star, like the sun, they will fade away slowly, okay? So, what is happening? The star starts to run out of fuel, okay? So, it doesn't have enough hydrogen to keep fusing into helium. So, gravity is going to start winning, right? The force of gravity is going to start to contract the star. Now, this actually means that because the particles get closer together, the core of the star superheats. So the place where I had all that helium being formed gets hotter. Now, this actually helps the star. The star now has enough temperature to be able to fuse helium into carbon, okay? The higher the heavier the element, the higher the temperature you need, because you need high temperatures to overcome the repulsion forces in between the nuclei. Remember that I have the nucleus of helium, which is made of protons and neutrons, so is a positive charge overall. So if I want to get two positive charges fusing together, okay, they need to go really fast in order not to be repelled by each other. So that's why I need to wait until the star starts to die in the first stage for gravity to contract the star further, so it superheats, and then I get helium to carbon, okay? Now, a star like the sun cannot do more fusion than that. So it will die after fusing helium to carbon, okay? Because gravity can keep compressing the star, it does not heat up enough to make further fusion, okay? So a star like our sun is going to become a planetary nebula after this stage where it fuses helium to carbon, okay? In the center of the planetary nebula, I have a white dwarf, which is a very dense star, a very dense and small star, okay? And this is how the sun is going to die, okay? Now, if I have other stars, for example, a white dwarf that is in a binary system, meaning that it has another star around it, because the white dwarf is so dense, it can actually engulf the other star. It can gather material from the other star. Now, what happens is, and again, I cannot give you the detail of the physics on this, but you learn that later on. And I actually have a video where I tell you about this critical mass. But what happens is, this star keeps gathering material, more and more material, but there is going to be a stage where it just is too massive, and this is where it reaches a limiting or critical mass. The star then becomes unstable and is going to explode, and this explosion is called a type 1a supernova. Every single type 1a supernova is because of a white dwarf. There isn't a binary, and it gathered way too much material from the star that is around it, so in the binary. It reached the critical mass and it became unstable and exploded, okay? So that's the type 1a supernova. Now, imagine that I have not a white dwarf, but a star that had a mass that is about 8 to 10 times the sun, the mass of the sun. This star can have more nuclear reactions because it has more material in it, and then the gravity is going to be higher because, again, I have more particles. So these stars can fuse into heavier elements, okay? They can actually start a fusion from helium, hydrogen to helium, just like the sun, helium to carbon, just like the sun, but then they can make further fusion, carbon to oxygen, oxygen to neon, to magnesium, to silica, to sulfur, and then it makes fusion into iron. Now the thing is, iron is going to be, the star is going to be unstable when it gets to iron, because the fusion into iron is not a reaction that releases energy. It is not exothermal, but instead it needs energy. So that means that if I'm trying to fuse to get enough heat to produce pressure to go against this gravity, and I get to a stage where instead I'm fusing, and instead of producing heat, I'm taking away heat, what is going to happen? I do not have enough force of pressure to balance with the gravity. So my star is going to become unstable and is going to collapse because gravity is going to be bigger than the amount of pressure. Now this collapse is super fast and violent. It can take about, I think, is a second or less than that. And this collapse is what we call a type 2 supernova. Okay, so type 1a supernova is when you have a white dwarf, a tiny dense star in a binary. Type 2 supernova is when you have a star that initially had a mass of about 8 to 10 times the mass of the sun, that can make more nuclear reactions and that can fuse into heavier elements. Now this star then is going to become a neutron star. Now the reason for that is because what is going to happen is the star is going to be collapsed, right? So instead of the planetary nebula, I get the outer layers of the star to be ejected to space, but in the center, just like before I would get the white dwarf, I would now get a neutron star. The reason for that is because gravity is going to try to compress the star completely. However, neutrons, they don't like each other, they repel each other, okay? So while a white dwarf is done because gravity cannot compress a star further, because electrons the electrons and everything that is in the nucleus repel each other, a neutron star is created when gravity is trying to collapse the star further, so further than a white dwarf, but the neutrons now, which were generated by combining the electrons and the protons that were there, they don't like each other, and they are going to as well try to repel each other. So this balances out the force of the pressure, and I get a star that is made of neutrons. So it's called a neutron star. This is a very dense star, even denser than the white dwarf, and sometimes neutron stars can rotate or spin. And if I can find that spin where they are ejecting the material, then I'm going to call that object a pulsar, okay? Now, just before I go on to bigger masses, let me just tell you that, you know what, when we're fusing these elements, heavier elements than helium, hydrogen, helium, and carbon, and I get all these elements, this is actually how we got the elements that we have here on Earth. It was when stars were alive, and then when large stars died, that they formed these elements. All elements up to iron were formed in stars during nuclear fusion reactions, okay? And then during the explosion, these elements were spread out in space. Elements above iron, so heavier than iron, they are created by the explosion. So again, the stars, the fact that a star is alive and then when it dies and it explodes, this is what gave the universe heavier elements. And this is why on Earth we have iron, that we have it even in our cells. We have carbon, that we need it again in our cells. calcium that we need in our bones, everything that we have is created by stars, okay? Without stars and without them dying, we would not have the critical components we would need to have life on Earth. So that's why Carl Sagan used to say, stars are us, instead of Toys R Us, you know, stars are us. Anyway, going to bigger masses, if my star is even more massive initially, it has 20 to 40 times the sun mass, then gravity, it will crush the star. Not even the neutron degeneracy, which is the repulsion force of the neutrons, is going to be able to counteract that gravity, is going to be able to balance out that gravity. Gravity crushes the star completely, okay? So my star becomes flat and is infinitely dense, so dense that not even light can escape. This is why I call it a black hole. So that's how I have a black hole, or how I get a black hole. And finally, we knew that in the early universe we used to have even more massive stars, okay? Now in these ones we just know that there is a massive explosion. However, I do not get to know more than that. So we have some stars that we may think they are just about to have these massive explosions. We only saw it in 2004, I believe, but it may be that we see more soon, okay? So in summary, if I have a small star, it is relatively small, spends a lot of time in the main sequence star, and then when the star starts to die out, it becomes a red giant. This is just before I get the planetary nebula. This is because the gravity cannot hold the star together after it's making this fusion of hydrogen, helium to carbon, okay? Then eventually the outer layers go and I get what is in the center, which is what gravity could compress and not let out, okay? And this is a white dwarf. Now a white dwarf can still shine. It's just that it doesn't shine as bright as the yellow dwarf, for example, or the beginning star. And then as it leaves and gives out energy, is going to become a red dwarf and then a black dwarf, because it's going to get dimmer and dimmer until there is no light coming out of it. So these stars, small stars, they are going to have a very long life, okay? In the meantime, if I have a large star, this star, although it's much larger, is going to only live about 10% of the life of a small star, mass star. So this star is about 10 billion years, this one is only about 1 million, for example. So it starts like a large star, okay? So it has more mass. It's going to be a blue star because the blue it means that I have higher temperatures, okay? Then this blue star becomes a blue supergiant and then a red supergiant as I keep getting the fusion into heavier elements. Then because I can fuse into heavier elements and I can get to iron, I get to a place where my star becomes very unstable very quickly, okay, relatively speaking, quickly. So what is happening is that the gravity is going to collapse the star entirely because the iron is not allowing the star to produce heat, instead it's taking heat away from the star. I therefore do not have the pressure to counteract the gravity. So I either get a neutron star, because gravity, I have the supernova going outwards, right? And then I have gravity compressing just the nucleus, the center, into a neutron star, or then I get a black hole, depending on how massive my star was initially, okay? So that is it about the life and death of the stars. I know that if you don't see the video, it may look like, what is she talking about? But that is the summary of everything. However, the video is really useful. I do recommend, and it's quite visual, so it's quite interesting. The video also talks about collisions of stars and failed stars, so feel free to watch that last 15 minutes as well if you want. Okay? But that is all that you need to know about stars. I hope it made sense. I do appreciate it's not as easy to understand as maybe other lessons, but it's because I am relying that you're going on that video, okay? So take care until my next lesson. Be happy and healthy. Bye!